we are discussing about Riemann-Stieltjes integral, and in the last class we have seen first mean value theorem for integral calculus, that is, let alpha be a monotonically increasing on closed interval a comma b, and f belongs to R of alpha on closed interval a comma b, that is f is Riemann-Stieltjes integral. Let m and capital M denote the infimum and supremum of the set of all f of x such that x lies between a and b, so that is nothing but the function values of f in the closed interval a comma b. Then it says there exists an r between the supremum and infimum of f such that integral a to b f d alpha is equal to r into alpha of b minus alpha of a, in particular if f is continuous on closed interval a comma b. Then r is nothing but f of c for some c belongs to closed interval a comma b. So we shall continue our discussion to the next result. So it says it's a corollary. It says suppose f and e are continuous on closed interval a comma b, and p of x is greater than 0 for all x belongs to closed interval comma b, then there exists a point c belongs to closed interval comma b such that integral a to b f of x a to p of x dx is equal to f of c into integral a to b p of x dx. That is, if f and p are continuous on closed interval a comma b and p is greater than equal to 0 on closed interval a comma b, then there exists a point c between a and b such that integral a to b f of x p of x dx is equal to f of c for some c between closed interval a comma b into integral a to b p of x dx. So let's see the proof of this. So proof. So x is equal to a to x p of t for all x to closed interval a comma b. Since p is continuous, given that p is continuous, p belongs to R on closed interval a comma b. Wait a second. Therefore, alpha is well defined. Since p is belongs to R, that is, p is Riemann integrable, this alpha is well defined. So further, alpha is monotonically increasing. In fact, if a is less than or equal to x, less than y, less than or equal to b, then alpha of y minus alpha of x is nothing but integration a to y p of t dt minus integration a to x p of t dt, and which is equal to integration it is x to y p of t dt, and it is greater than or equal to 0 since y is greater than or equal to 0 on closed interval a comma b. Therefore we can say x less than y implies alpha of x is less than or equal to alpha of y, that is, alpha is monotonically increasing. Since f is continuous on closed interval a comma b, since f is continuous on closed interval a comma b, f is continuous on closed interval a comma b implies my belongs to closed interval a comma b. It belongs to R of alpha on closed interval a comma b. Use for this alpha monotonic function alpha. Then my first mean value theorem. Then my first mean value theorem, integration a to b f d alpha is equal to f of c into alpha of b minus alpha of a, using my first mean value theorem for integral calculus, where c is some point, where c for some in closed for some c in closed interval a comma b. So this implies integral a to b into b f d alpha is equal to f of c into a. Now alpha of b minus alpha of a is nothing but it is a to b of t dt, because alpha of a is nothing but integration a to a, it is 0, since alpha of a is equal to integration a to a p of dt is equal to 0. So we observed that alpha is differentiable on closed interval a comma b, and alpha dash of x is equal to p of x on closed interval a comma b. Therefore consider integration a to b f alpha, which is equal to integration a to b f x d alpha of x, which is equal to integration a to b f of x alpha dash of x dx, which is equal to integration a to b f of x p of x dx, because my alpha dash of x is nothing but p of x, so it is p of x dx. So from comparing this one, that is, we have integration a to b f d alpha is equal to integration a to b f of x p of x dx, and we have integration a to b f d alpha is equal to f of c into integration a to b f p of t dt. So using these two, we get integration a to b f of x p of x dx is equal to integration a to b f d alpha, and that is nothing but integration f of c into integration e to b p of t dt, or we can also write this, that is f of c into integration e to b p of x dx p of x, hence the result. So we shall continue to the next result. So it says second mean value, it's the theorem. It says it's known as second mean value theorem for integral calculus. Second mean value theorem for integral calculus. So say suppose that f belongs to R and f of x is greater than or equal to 0 on interval a comma b, and g is monotonically increasing function on closed interval a comma b, then there exists a point zeta in closed interval a comma b, such that that integration a to b f of t g of t dt equal to it is g of a into integration a to zeta f of t dt plus g of b to integral zeta to b of t dt. So just solve this, that is proof. So define h of x is equal to g of a into integration a to x f of t dt plus g of b into integration x to b f of t for all x closed interval x comma b. Note that the function x going to integration a to x f of t dt is continuous. Wait a second. Is continuous. Also integration x to b f of t dt is equal to integration a to b f of t dt minus integration a to x f of t dt f of t dt. X going to and also x going to integration x to b f of t dt is also continuous. X going to g of b integration x to b f of t dt is continuous. Therefore my h is also continuous, that is my h of x is also continuous. Therefore this h of x is also continuous on interval a comma b. This one is continuous, this one is continuous, hence this h of x is continuous on closed interval a comma b. Also if you observe h of a is nothing but g of b into integration e to integration observe h of a is nothing but g of a into a to a will become 0 integration, so it is g of b into integration a to b f of dt and but a into it is integration t dt f of t dt. G is monotonically increasing, since g is monotonically increasing because since given that g is monotonically increasing, g of a is less than or equal to g of b, which is less than or equal to g of b, but for all t belongs to closed interval a comma b. This implies g of a into f of t less than or equal to g of t into f of t, which is less than or equal to g of b into f of t for all t belongs to closed interval a comma b, because given that my function f is greater than or equal to 0 on closed interval a comma b, since f is greater than or equal to 0. Now taking integration, that is this implies integration a to b g of a into f of t dt less than or equal to integration a to b g of t into f of t dt, which is less than or equal to integration a to b g of t into f of t dt. So using my integration properties, that is now if you, so this is nothing but g of a into using the property of integration, this is nothing but g of a into integration a to b f of t, that is nothing but h of b, so which is less than or equal to integration a to b, so it is g of t f of t dt, which is less than or equal to h of a, because there is nothing but g of b into integration a to b f of t dt. Now since h is continuous on closed interval a comma b, since h is continuous on closed interval a comma b, by using intermediate value theorem, there exists some zeta belongs to closed interval a comma b such that my h of zeta is equal to integration a to b g of t f of t dt, that is that is integration a to b g of t into f t dt, which is equal to h of zeta, and that is nothing but g of a into integration a to zeta f t plus of t into integration zeta to b f of t dt, f of t dt. Hence the proof. This is the second mean value theorem for integral calculus.